we're just going to go straight into lecture once we solve this. So this is actually this problem here. So suppose that you had this many grams, right, of sodium carbonate. It's dissolved in 250 milliliters. Excuse me, not sodium carbonate, oxalate. This is going to be dissolved in 250 milliliter volumetric flask, and so your total volume is 250 milliliters, right? If 10 milliliters of the solution required 48.36 milliliters of potassium permanganate, solution for titration, what is the molarity of the permanganate solution? Okay, so you have a molarity there, don't you? All right. First thing you need to do is you actually need to figure out the molarity here. So can I use grams to figure out molarity directly? I need to convert that to moles, right? So the first thing I need to do is I need to take those grams. This right here is everything you need to just go to your periodic table and add these things up, right? You add these things up, it's going to be 134 grams per mole. Okay? Divide grams by your grams per mole, that leaves you in moles. Whenever you have molarity and you're working in molarity, well, that is moles of solute divided by liters of solution, right? And so all we have to do is we just divide by the moles number by the liters of your total solution. That's that 250, isn't it? Okay. In liters, that's 0.25. Okay. That's going to give you your molarity. You'll notice that that was one of the options that was on that chart, wasn't it? Okay. Okay. And so that is the molarity of your standard solution. Okay. That's what you're going to measure things against, right? This is a very stable buffer solution that you can make. You can dry that this compound out very well. It's a salt. And it's not super hygroscopic like sodium hydroxide is. Okay. All right. So once we have this molarity, well, you can actually use M1V1 equals M2V2 to figure out the next step. You may have seen this formula restated as MAVA equals MBVB. Okay, back in general chemistry. All right. All that's saying is that if you solve molarity out to moles, well, then that's your exchange, right? That's your stoichiometry number. Okay. And so if it's a 1-to-1 ratio for this neutralization, then it would be 1-to-1, right? If it's a 1-to-2 ratio, then you'd have to use a 1-to-2 ratio, right? Okay. So one of the first things we have to figure out is, well, how many moles of the potassium permanganate would you need to neutralize the oxalate? So how many moles would you need there? Okay. So if we look at this reaction, okay, that's actually reaction 7.1 in your book, in case you're wondering. It requires 2 moles of permanganate for every 5 moles of oxalate. See this portion right here? That's the sodium oxalate. How do I know that it's a 2 minus oxalate? Because we're going to lose the 2 sodiums, right? Okay. Anything with sodium is a good electrolyte, strong electrolyte. Okay. So the first thing I need to do is I need to figure out how many moles am I going to have in this solution if I take 10 milliliters of this oxalate solution, right? And so I have this molarity here, okay? And I'm going to take 10 milliliters out of it, so that's 0.010 liters, right? Everybody good with that? Did I lose anybody up to this point? Okay. Okay. This would be the number in moles, by the way. You can put that in millimoles, by the way. Sometimes it's very easy to work in millimoles because if you're going to use a bunch of numbers in like milliliters and stuff, the millis can cancel. Okay? Everybody knows you can cancel the prefixes separately than the units, right? Okay, so like if you have 2 millis, one over another, right? One divided by another, you can cancel those millis independent of your units, right? Because the prefixes are just 10 to the thirds numbers, right? That's all they ever were. Okay, so once I get this is the millimole number right here, by the way. You'll notice that that was another option in your options. I literally just took your options from the stuff you would have worked out through it. Notice that millimole is not a concentration, is it? Okay, that's a moles, right? That's an amount, so not a concentration. Okay. Okay, so we're going to take that millimoles number. We're then going to try to get that from oxalate into potassium permanganate, right? Or rather, the permanganate ion. Okay, so we're going to then take that ratio, reaction 7:1, 2 moles of permanganate for 5 moles of the oxalate. We're going to get here our moles number right there, and that's going to be 0.04253 millimoles. Okay, see, that's just a little bit different. That's that ratio here, isn't it? Okay. All right, so the next thing we take is we have millimoles of the potassium permanganate, right? That we would have used to neutralize it. So what we need to do is we need to divide that by the volume, okay? That will give us concentration. And so we take our millimole number, we divide it by milliliters. Notice the milli will cancel, leaving us in moles per liter, which is molarity, right? Okay. And so that's the final answer right there. Everybody good with that so far? Yeah. Okay, if you would like to re-answer, I will allow that. There are one person got it wrong. So if you want to re-answer, feel free. Can you see it now? All right, everybody is right. Fantastic. Okay, we will start doing the lecture now. Okay. Now, this is going to be the first chapter that's directly titrations. The previous chapter was the equilibriums, which is and solubility, which is what titrations depend on, right? And so when we're doing titrations, these are typically going to be a volumetric analysis. That's the procedures that measure volume of reagents that need to react with our analyte. Notice that as opposed to gravimetric analysis. Gravimetric analysis being the weights, right? That we're doing. Titration is going to be the procedure in which one substance, the titrant, is carefully added to another substance, the analyte, i.e. the one you're analyzing, until complete reaction has occurred. The titrant, substance added to the analyte of the titration, usually you deliver that one in the burette, though you do not have to. You can do it in reverse, actually. However, because you typically know the titrant the best, and you know what its standards are and what you need to avoid, I would recommend using your titrant nearby burette, unless you know you do not need to, okay? Like one of the examples, for example, if you have something very, very concentrated and you put it in your burette, it can actually plug the burette, okay? Another thing is if you don't know what you're putting in, it can react. It's Nalgene is that plastic portion. And glass can be reacted with too. For example, did you guys know that when you put NaOH in your burettes, you're actually reacting with glass? Okay. So you actually dissolve a little bit of the glass. That's why it will fuse the tip if you don't clean that out really well. That's why you never put a high concentration NaOH solution in your burette. Okay. Because they're quite expensive, actually. We calculate the quantity of the analyte from the quantity of the titrant consumed. So some of the titration reaction attributes, quantitatively complete, i.e. you're typically going to get 99.9% or better amounts. You may notice that the gravimetric analysis that we were doing probably not going to be complete, right? Like, who here thinks the gravimetric analysis you got 99.9% or better of that error? Probably not, right? It's difficult to get all of it to the next stage, especially if you have to do reactions and flasks and stuff, right? If we could shorten that up, we could do better. Very rapid, has a well-known stoichiometry, accurate means to estimate the equivalence point. You may have noticed that titration, you could actually just like off that first one, calculate out where you should end for all the rest of them, shouldn't you? And then you know about where you should end, and you can very carefully do the rest. Okay. Rapid is a bit of a thing. It is rapid compared to most like gravimetric, right? The titrations were much faster than the gravimetric were. Okay. But as compared to a lot of instrumental methods, these are pretty slow. Some of the common titrations are going to be acid-base reactions. That's the ones you have all typically done before. That's the one we did in the lab for the last lab. Okay. The oxidation reduction reactions you can also do. Has anybody actually done any titrations like that yet? Every now and then you see somebody do those in the general chemistries. They can actually work extremely well, but because you're doing redox reactions, they can be a little dangerous. So, complex formation reactions and precipitation reactions. Anybody done a precipitation reaction with titration? No. The nice thing about precipitation reactions is you'll get a precipitate out, right? Which can be pretty easy to see, though you have to look very carefully. Because just because you're making a precipitate does not mean it's going to be on the bottom of the flask, right? But it does mean it'll get cloudy. Now, this is a typical setup for a titration. There are also things called auto titrators, okay? So in a normal titration, you use a burette, stopcock, and what you'll do is you'll deliver it, right? An auto titrator would actually have a mechanism here that drips these, and then you have to have some sort of detector that will turn that off, okay? All right, so what is the equivalence point? So this is the point in the titration at which the quantity of titrant is exactly sufficient for the stoichiometric reaction with the analyte. And so at the equivalence point, you have consumed both of your reactants, whether they're acid bases or redox, right? And you have converted them all to the final product. Okay, and that is your equivalence point, right? Is this necessarily something that's really easy to see? Well, for this reaction, it would be reasonably easy to see, right? Okay, so you go from being purple, right? And then you reduce the color, and eventually it gets colorless, doesn't it? Okay. As you add more of the analyte, what would happen to the color? Yeah, analyte would not cause a color change, right? But as you add more titrant, what would happen? So if we start with this analyte here, right? We're adding titrant, drip, drip, drip. When the drips hit the solution, what happens to your colors? You get a little bit of burst of color, right? A little purple burst. Okay? But as you mix it, what happens to your color? Yeah, it goes back to clear, doesn't it? Okay? And so we drip, 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 drip. We hit our endpoint, our equivalence point, excuse me. Is there any actual change at the equivalence point time? If we have this at exactly equal, we've consumed both of these. What would that look like? Would it have any color? It wouldn't have any color, would it? It'd still be clear. Okay? You would have a bit of a hint, and that would take a while for the purple color to disappear, wouldn't it? Because it has to find the analyte in that solution. Okay? But you would actually see nothing when you hit your equivalence point, would you? That's true for most equivalence points. Okay? And so we go past the equivalence point now. Drip, 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 drip. We're adding more of the titrant. What's happening to the color? Purple. And we'll get more and more purple, right? We'll get up to the coloring of basically our titrant if we added enough, right? Now, do you see purple immediately? If I put one drop of food coloring into a container that's like a liter, am I going to see it? No, I'm not going to. No. So I usually have to put multiple drops, right? And then I'll start seeing it. And so typically what you do is you actually need a 10 times concentration differential to see things. And so you're going to have to add like a few drops of this to actually see any color, aren't you? So you're going to overshoot your equivalence point. Okay? And that's in a perfect equivalence point. Like literally you're just looking for the color of your thing you're adding. Right? Okay. Now, the let's say that's unknown here has 5 millimoles of oxalic acid. The equivalence point is reached when you add 2 millimoles of potassium permanganate have been added. And that's because this is the reaction for this. So this is the formula for this reaction, excuse me. And so this is going to be a 5 to 2. That's where that number came from, by the way. That 5 to 1 or 5 to 2 number. Okay. Now again, the equivalence point, this is a theoretical result based on stoichiometry. You'll probably never actually be able to detect these for the most part. You'll get pretty close if you choose your endpoint very well. Okay? And that's kind of the best you can do. The endpoint is going to be the actual measurement point at in a titration. When you have a sudden change in that physical property, you could have color right, you could have electrical conductance, which is what most auto titrators use, by the way, in case you're wondering. Color, you can also do an auto titrator for. That's a visible light probe that you'd put in. But you need some sort of physical property to change so you can actually detect this, right? And so that's going to be your endpoint. When you can actually see it, you detect it, and you end the titration. Okay. So, does anybody have any questions? Did I lose anybody in that? Fantastic. Now, one of the things I need to mention that the indicator, sometimes you're going to have to use some sort of indicator, which will give a color change, right? Not everything has colors to it, right? In fact, we did an acid-base titration and we used an indicator, didn't we? Okay. So the indicator, that's going to be a compound. Typically, it's going to be a dye of some sort where you're going to have a color change at a specific pH level, or you can have a specific redox reaction that sets off color change. But some sort of dye typically. And usually it's going to give you an indication because of the color shift. Okay. So this will change abruptly if you've done a good job choosing an indicator. That's going to be near the equivalence point that color change will change. Okay. If you've done a poor job, then your endpoint and your equivalence point are going to be very far apart, right? All right. Now, again, you can do electrodes. You can monitor the absorption of different various forms of light. There's actually a few other ones you can do. But they are far, 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 far less common and have been falling out of favor more and more. Okay, because spectroscopy and electrochemistry has just gotten so good and cheap. So they've been quickly coming out, being removed for this test. Now, titration error, the difference in the amount of titrant between the observed endpoint and the true equivalence point in a titration is your error, of course. Blank titration, you're going to carry out the same titration procedure on similar solution without your analyte. This will actually give you an estimate of your titration error. This would have been a very handy thing if we had some time to do in the lab we did, where you just take literally some of your indicator and do your titration. But we had different indicators to compare in that case. So the volume of the titrant needed in the blanks titration should be subtracted from your volume needed to titrate an unknown. Let's think of an example real quick. Did anybody notice the indicators actually had a little bass in them? So what's that going to do to your titration? Yeah, as soon as we add a couple, like 2 to 4 drops of indicator, right? It's as if we added 2 to 4 drops of our base, isn't it? Okay, because they were actually pretty similar concentration to our base that we're using. So in those cases, you would actually have a bit too fast of a change, right? Now, in most of your cases, this was probably counteracted by the fact that you can't see the color that well, and so you were taking too long to note the color change, right? Because our human eyes are only so good, right? But let's talk about primary standards. So the analytical result is going to depend on knowing the amount of one of the reactants. And so it's very important that you can very accurately measure the amount in one of your reactants. This is going to be where primary standards come into play. So this is going to be a reagent that's pure enough and stable enough to be used directly after weighing. The entire mass will be considered a pure reagent. And so, for example, typically these would be 99.9% or better pure. And so you don't have to have a lot of impurities. If you do have impurities and they don't take part directly in the reaction, you can actually correct for those. But it's better to just start with something pure. And there's plenty of primary standards for most titrations that you can do this. One of the most important things is this should not decompose during storage. If it decomposes during storage, you have a major problem, right? Because every single time you use it, it's going to be different, isn't it? Okay. This is a very big problem. Notice in these previous ones, we used potassium permanganate. Anybody know what happens when you set that under light? It changes. Yeah. So, you've all used potassium permanganate at some point during general chemistry. Okay. You may not have realized it was like this purple brownish solution that you're using. And the teacher was like, be very careful with this. That was potassium permanganate, okay? I.e. the permanganate we've been talking about here. When you're on a room that has light at room temperature, this is actually going to decompose pretty quickly, actually, if you have a clear bottle. And so your potassium permanganate would decompose within like 3 to 4 days usually. You'd have a very significant change, and it would turn from a purple color to like a brown color with a bunch of specks in it. Okay? When you guys use potassium permanganate, did it have a bunch of like brown specks in it? Yeah? Okay, they made it fresh then. That was very nice though. Okay? And so this is actually one of the reasons that like potassium permanganate can actually be quite difficult to use. You typically have to store it as the solid and make fresh solutions every time. And when you store it as the solid, you need to make sure you use the container that, number one, you need to keep it in relatively dry conditions. And number two, you need to actually keep it away from light. Okay? That's why if you ever see them, they're typically stored in amber bottles. Okay? Reduce the amount of light that they get exposed to. They're stabled when dried by heat or vacuum. Heat is typically the like primary standards that most people would want to use. Vacuum can help out the drying procedure, and you can dry some of these by vacuum, though you usually need some degree of heat. However, that's a very expensive way to dry things. Okay, so you really need to have some financial means in that case. Vacuums take a long time to actually vacuum down. Okay. Did anybody notice what I did to your Trish standard after you guys had it open for a while? Okay, where'd you get the Trish standard last time? It was in the oven. What was I doing? I was taking your standard, right? And I was drying it. Okay. Okay. So Chemicals are sold under many grades of purity. A few chemicals are sold in high enough purity to be a primary standard grade. It's not exactly common for them to be sold that way, though you can get many different chemicals that way. Reagent grade chemicals meet purity and requirements that are set by the ACS, Committee on Analytical Reagents. So reagent grade is the grade that this would be really good for a reaction. Okay. This right here is actually the ACS reagent grade level of impurities. It is not the highest grade. There are higher grades. In fact, there are 2 to 3 higher grades depending on the manufacturer. Okay, but it is usually acceptable grade for like most like academic labs and most commercial property labs. Trace metal grade reagents, they have extremely low impurities, very important for trace analysis that are like less than part per million. And so this would be one of the highest grades you can get. Okay, it has such a small amount that you're not going to you're going to be able to do analysis that would be part per million. Okay. Appendix K actually lists the primary standards for many of the different elements. So if you go to Appendix K, you can actually figure out primary standards for a variety of different purposes. It's actually one of the most useful things if you ever end up in like a corporate or government type analytical position where you might have to design new tests. It can be quite useful. Now, there's a few different things you may have noticed that I've been cracking down on everybody a lot more on. Some of this stuff we don't really have around here, and it's just difficult for us to store all this extra glassware. Okay, but these would be things you'd want. Number 1, you avoid putting the spatula in your reagent bottle. You pour chemical into a clean container or weighing paper. You then dispense it from that clean container. So when I had you do the tris, did anybody notice what I kept telling you to do? You put it in the weighing boat, right? A clean disposable container. And then you take that over to the balance. You get the weight from that by pouring it directly into the flask you're going to do the measurement in, right? Okay. So you never pour unused chemical back into a reagent bottle. Hopefully everybody knows this, period, that's just not acceptable practices. You replace the cap on a reagent bottle immediately to keep dust and moisture out, depending on how sensitive you are to moisture. You may have noticed I kept chasing you down and being like, what are you doing? Leave my cap off. Keep the cap on. It's not just dust, by the way. Does anybody know what it actually looks like around you if you were to use a particle detector? So if you were to detect the particles around you, you shed skin cells off you all the time. And in fact, the 3-foot area around you is full of like a haze of skin cells. Okay? And so everything you come within 3 feet of, and you are covering in yourself. Okay? So that tris bottle now has a little bit of skin from all of you. Just a bit. Now, never put glass stoppers from liquid reagent containers on a lab bench. You never want to touch those. What you want to do typically is you would actually take your fingers, and let's say this was the cap for this bottle. I take the cap off. I keep it like this in my fingers. And then I manipulate it. Everybody see that? That's how you actually want to keep a cap for a container. Okay? And so you take that little flange on the top and you keep it between your fingers and use the rest of your hand to manipulate the container. Okay? And that'll keep you from having to put it down on the bench all the time and contaminate it with the bench, right? And anything else around it. If you have to put it down, what you'd want to do is, some are designed with flat tops that you can actually rest like this. Okay? And that's kind of nice. It makes your life a little easier. However, the ones that are not designed that way, you'd want to take some weighing paper. Put it down under, and then place it down on weighing paper. And then you'd always dispose of it each time when you're done with it. Store chemicals in cool, dark places. Do not expose chemicals to unnecessarily sunlight. Sunlight is a real killer, and it does penetrate through windows to some degree. Okay? The reason sunlight's a real killer is it has quite a bit of the high energy lights in it. Not enough to really cause a lot of damage to you most days, but like that UVB, UVC energy light can cause reactions to occur that you do not want to occur, okay, and cause these things to break down. Now, many of the reagents that we use as titrants are not going to be available as primary standards, and you probably wouldn't want to use them. Like most of the primary standards are not really ones you'd want to use to do titrations with. Either it'd be very expensive, it could be extremely difficult to do because they're more reactive, it could be that they clog things up when you try to use them. And so what you end up doing is you actually standardize another solution usually. So typically what you would do is we were actually doing a standardization that in titration, that's what we were doing in lab, okay? So you would take like an HCl or an NaOH, and then you'd use a primary standard to do a standardization of it. And so you'd prepare your titrant with approximate concentration. That's why I gave you one that said 0.1, right? Notice it didn't have any other decimal points. It only had one sig fig, right? Okay. And then you use that to titrate a primary standard that's been dried, and you know the mass of two, right? That's why we measure that in analytical balance, so we can get more significant figures, right? And then the method would determine the concentration of your titrant. The titrant is going to be your standard solution. The validity of the analytical result is ultimately going to depend on knowing the concentration of your primary standard. And so your primary standard will set the concentration of your standardized solution, which should typically be something like an HCl, like you all used. Okay. Is that making sense so far? Okay, so direct titration. This is the one you've probably done the most of. You may have done a back titration as well, but we'll see. So this is going to be where you add titrant to the analyte until you complete the reaction. Back titration is going to be adding a known excess of a standard reagent to the analyte, the standard excess with the second standard reagent. So let's say we took something that's basic, like an antacid is what this is done on a lot. Okay? So antacids are basic, right? They neutralize HCl. Okay? So what we do is we put in a bunch of HCl, excess, more than it would require to break down and use up all the antacid. Okay? And then we would take that excess and we would titrate it backwards, back down, and neutralize all the excess HCl. Okay? So if we know the amount of HCl, right? So we have this HCl. It has 0.500 moles. Put in. Okay? And then we have our antacid, right? And we don't know that. Okay? Let's say we used 0.300 moles of NaOH. Okay? Well, how many moles of the antacid? Assuming it's a 1-1. Bless you. Yeah, 0.2, right? What's the difference? Okay? And so then we know 0.200, right? And that's all a back titration is. It doesn't have to be acid-base. It can be anything. But you just use two titrants instead of one and back titrate to get your result. A survey titration. This is your quick titration performed to get an estimate of the equivalence point and familiarize with the color change of the indicator. Remember what I was saying, that first one you need 7 total? And so you use the first one to do a survey titration. Okay? And so you very quickly run through it. All you're really looking for there is a general idea of where your endpoint might be. And you're looking for what sort of color change are you looking for. Okay? Typically, most people will keep this survey titration, set it to the side, and then they'll have an example of what the color change ends up at. Okay? So they know what they're looking for. And they'll use that as sort of a matching key. And then they'll take all their titrations. They don't typically clean them out as they do them. They just set them aside next to that survey so that they can see if they're gradiating on color. If you're changing and gradiating on color, then you have an error in there, don't you? You don't have the same SOP every time you're doing this. Okay. Okay, so gravimetric titration. This is going to be a titration in which the mass of the titrant is measured instead of the volume. And so you would add your titrant, and then you would actually measure out the mass each time. Okay. So your titrant can be delivered from a pipette or syringe. And what you would do then is you can just reweigh it every time. And that difference in the weight is then the difference of the mass you've delivered, isn't it? Okay. And it's going to be moles of reagent per kilogram of solution. Your precision is improved with from the 0.3% with the burette measurements to a 0.1% using a top-loading balance. And so this is actually a more precise way of doing this. But as you can imagine, it does take more time. Like, significantly more time, right? You can also set it up, by the way, using burettes and just a normal top loading balance. So if you set up your flask down the bottom on the balance, you can actually do this. Okay? So as you add, you can actually measure the mass you're adding each time. So, the titration calculations. I think everybody's pretty familiar with these. Realistically, all it is you have a molarity number typically, right? That molarity number already had moles in it, didn't it? You're using the burette to get volume, aren't you? And so you have, moles and moles that comes out of that molarity, moles over volume. And once you have moles, well, you just need to use the stoichiometry of the reaction, don't you? And that will give you your moles of your product. Okay. And so right here, this would be a calcium in urine. And so you can actually use oxalate, react with the calcium. This would give you a precipitate. And so you can collect up all the calcium oxalate. You can then titrate it with potassium permanganate. This would then allow you to detect the amount of calcium in the urine from the calcium oxalate, right? Notice that would just be 2 stoichiometric steps, wouldn't it? Okay, this is actually the problem we were looking at before. Okay. And we got our answer, right? Does anybody have any questions about that problem in light of the new perspectives? Okay. All right. I think we need any more there. Is anybody having any questions about these titrations at all? Okay. Okay. So let's talk about some of the propagation of uncertainty in these titrations. So 2 burette readings, you have the initial and final volume readings whenever you do a titration, right? And so you're going to have 2 sources of uncertainty. And so you are going to have to, because you did that subtraction, right? You did the final mass initial to get the mass, the amount that your burette delivered, right? And so you're going to have to use the U titration. It's going to equal the U initial squared plus the U final squared. And then that would be plus the U squared of the endpoint. Notice again, there's that error due to the fact that the endpoint is not the same as the equivalence point, right? And so this is how you would then include that error. Okay? That comes from blank. You'd want to run a blank to get this. Okay. Okay. So the relative uncertainty would then be the U titration here, the uncertainty of the titration, divided by that difference in volume, and then times 100% to get a percentage, right? Did I lose anybody right here? So you take the difference between those volume measurements, right? You would also subtract off the endpoint correction, which is this one's value. And this is just that chapter, the propagation of uncertainty table. This is just that format. We're doing this for an addition subtraction, so we use the squares method. Okay, now titrations are oftentimes viewed as titration curves. This is a very convenient way to view them because you can get a lot of data out of it actually very quickly. So this is going to be a graph that shows the concentration of your reactant or some sort of physical property of the solution, and it will vary as you vary the reactant amount, the titrant that you've added to the analyte. Most often, these are actually just the amount is just shown as milliliters, but you don't have to do them in milliliters. You can do them in moles, you can do them in all sorts of units, masses, etc. One of the cool things is graphically, this actually demonstrates a lot of the results that you would actually get from doing calculations. And so you can find those results extremely easy using a graph. Okay. It also can really help you understand the chemistry that occurs during that titration and what exactly is actually going on there. Okay. So you can also learn how the experimental control can influence the quality of your analytical titration. Your sharpness of your endpoint is actually two main points that tend to dictate that. That's the concentration of the analyte and titrant. If you have a very high concentration, what would happen to the sharpness of your endpoint? Does anybody know what these graphs look like, by the way? So these graphs look like this. Like that. Okay. That'd be a very sharp endpoint. See how it's almost vertical? Okay. Endpoint that is not very sharp would look like this. So yeah, it's very slanted. And so your endpoint happens over a wide space, right? Okay. So what would cause these to be different like that? Hey, Joe. From what I heard about your titrations and the biochemistry. So why do you get a very slanted, not very sharp endpoint? Got it. Yeah. So if your concentration of your titrant is too high, you can get a very, this will change the sharpness of your endpoint. Okay. This would be like a 0.1 concentration titrant being used on something else like concentration of 1. So each of these drops is going to be very close together, right? And you won't be able to see them. It'll literally look like a line. Okay. Let's say that we'd use something that's like 1 molarity each. Well, you'd get drops like this, right? And so if we actually followed this with something like that, what we would see is something like this. It would look like this. See that? We'd end up skipping almost all of our endpoint, okay? Because our concentration is too high. Now, would you always want to just do like 100th, a millionth of your concentration for your titrant? Oh, if you do it too small, you're never going to finish, right? Like, let's say I did something a millionth my concentration. I would need like 1,000,000 drops to get this to finish, right? Am I going to be able to deliver 1,000,000 drops? Even time-wise, let's forget time-wise. Like, is 50 milliliters going to be enough to deliver 1,000,000 drops? Each drop is about 1/20th of a milliliter, in case you're curious. So 50 milliliters would be about 1,000 drops, give or take. Okay. So concentration of your analyte and titrant and that difference between them. The other thing that happens is the size of your solubility product, okay? So that solubility product will actually change where this part is, which is normally like an acid base, would be a buffer. This is the buffer region and acid and base, by the way. But whenever you have a difference in KSP, that KSP does shift this entire region. And so it would cause this part to shrink. So let's say we had different KSPs and pretty much the same thing we're looking at. We could have something like this. What do you notice about the endpoint there? The more area it covers, the sharper it is, isn't it? Okay. Okay. That concentration, it varies over orders of magnitude. So you actually have to use a P function wherever you're looking at these things typically. And so that would be a px, which would be a negative log base 10 of whatever you're looking at. Okay. You already know this scale because we typically use pHs for this, right? And so this was always like pHs we'd been using here. And then milliliters of our titrant, right? NaOH, HCl, whatever. And so you've already gotten used to it. Okay. However, this could be PE, where you have like the potential difference between two electrodes. And so you're looking at a logarithmic scale of those. Okay. Okay. Now this right here, this would be a reaction titration where we have 100 milliliters of 0.01 molarity Cl minus and 0.04 milliliters molarity of Ag plus, the silver. Everybody recognize that reaction, by the way? Remember your silver nitrate reaction? You add a drop of silver nitrate, see if it got cloudy. That's the same reaction. You'd be looking for the same thing here, right? Okay. Okay. And so if we look at this KSP right here, so this titration reaction is actually their version of this distillation, which the KSP is 1.8 times 10 to the negative 10. So our equilibrium constant of this would be extremely large, right? These bind together extremely well, which is why you did this. Because it binds together extremely well, you were looking at something very sensitive if you were to do a quote-unquote titration, right? In fact, we were so sensitive, right, that single drop from a titration caused our product, right? And that's why we used it for that. So the equilibrium will lie far to the right. Each aliquot of silver is going to react nearly completely with chloride. And so at the equivalence point, you're going to have a sudden increase in silver because you'll have no chloride left to consume to add the Ag. And so this would have an extreme endpoint. You basically would just jump one to the other state. Okay? It would barely take, drops would probably be more new action. Okay? This would be like a fifth of a drop would cause this sort of situation. Right? Your one drop probably overshot it by a fair amount. Okay? Well, a drop. Now, so what volume of silver titrant would actually be needed to reach the equivalence point? The VE, the volume at the equivalence point. So this is actually the stoichiometry right here. It's 1-to-1 stoichiometry. Everybody see that okay? And so if we did the 0.1 molarity right there of the chloride and 0.04 molarity of the silver, we put in our volume. So we have the volume 0.100 of the chloride, concentration of that. Notice that's going to get us into moles, right? In this case, the moles of silver is a 1-to-1 ratio here. So notice it ends up being set up a lot like M1V1 equals M2V2, right? It's the 1-to-1 ratio. And so we put our molarity here. We divide that over. Notice that this volume then is going to be 25 milliliters. That's going to be where you should expect your equivalence point, right? And so whenever we're looking at a titration, we always have the area before our equivalence point, okay, which is this part right here, right? Before equivalence point, okay? And then the next area would be at equivalence point, right? Okay. It will broaden out depending on our conditions, okay? Technically, it should just be the dot around it, but sometimes it's not quite that sharp. And then we have after equivalence point. Notice this includes this little part right here. See that? Before and after equivalence points can include these little climbing parts. Okay? Okay. So we have our three distinct zones. We have before. What are we looking at before equivalence point? Are they equal yet? Not equal yet, right? What do we have more of at that point? Our analyte, don't we? We have more analyte at that point. Okay? Okay, equivalence point, we have equal moles, right? Or at least stoichiometrically they are equal. Okay? Okay, what is after equivalence point then? What's in excess? The titrant's in excess. Yep. So we've added excess titrant at that point. Okay, so if you've added 10 milliliters of that silver at this point, what are we actually looking at? Well, we're looking at before equivalence point, aren't we? We haven't added 25 yet, have we? And so what are we going to see? Well, this silver is going to use up chloride, right? We'll produce silver chloride, and we'll use up some of the chloride, but there'll still be some of that chloride that remains. So the titration reaction is going to go to completion, and we'll have the silver chloride will redissolve. The solubility of silver is going to be dictated by the concentration of your free chloride that remains in your solution. And so this would actually be the exchange of that formula. Notice it's just the KSP written out so that the silver portion is all on one side, right? Okay. Okay. Now, the unprecipitated chloride, how many moles of that would we have? All right, so we're going to have whatever amount got used up minus subtracted off whatever amount we started with, right? And so we take what we started with minus what we got used up from that silver addition, okay, which is right here. Notice that's that 10 milliliters. And then that's going to give us the moles of the chloride remaining. Now, notice that you have to be very careful about one thing here. Once you get the moles of the chloride, well, if you're doing a titration, you're adding volume, aren't you? Okay? And so your concentration is always going to have that, extra volume getting added to the bottom. Okay? So we would have started with 100 milliliters, right? And then we end with, 110, don't we? Can everybody see that okay? Because we added an additional 10, didn't we? Okay. Okay, how do we get the silver then? Well, that's just going to be this KSP formula. And so we go ahead and plug these numbers in the KSP formula. So that right there is the KSP. That's divided by that chloride number. And then that's going to give us our silver number. Note that you're typically going to want to look at this in terms of P, so negative log of those numbers, because they're going to be very small. Okay? And so you take negative log of that number, and that gives you 7.48 for the P silver. This is just a streamlined method for this calculation. We've taken all the parts of the calculation, we've just plugged it into one single formula. Or another way of thinking of that is, how you do the railroad tracks? You ever did those? We just took everything and put it in one railroad track, right? So we can do the whole calculation in one go. Okay. And so this is the fraction remaining right here. This is the original concentration. This is your dilution factor, change in your dilution, right? Notice the 100 to 110 milliliters now. Okay. And that makes these problems very quick to calculate. Okay. Hey, we had 2 sig figs here. Why is that 3? What's going on? It's the mantissa, isn't it? When we do significant figures going through a log, what happens? The number of sig figs that go into the log is the number of decimal places that come out, right? And so remember, this number corresponds to that one, okay? When you have the number that comes out of the log, this number here is this number, isn't it? This is not a significant figure in terms of uncertainty. This number is coming from the power, okay? So your number of sig figs is actually here, which is the digits in your mantissa, okay? The decimal places. All right, so let's calculate the PAG plus when the volume AG plus, the volume added from the burette is 25 milliliters. Is everybody okay with my volumes here? See, these are just volumes with what they are in the subscripts. Hopefully you start getting kind of confident in that, used to it. Going, oh, yeah. This is how in science we actually like put all our variables. We don't just put volume 1, anything like that. You'd want to put volume what it is. Okay, go ahead and start working on that. Make sure you can do that calculation. So the first thing you always want to check, are we before equivalence point, at, or after? So the equivalence point was at what point? 25 milliliters, right? So we're before equivalence point. I'm going to give you one more minute. Try your very best. Make sure you actually try it out. You can use the accelerated formula if you want. Okay, let's go ahead and start going on. Hopefully you got to try out the formula a little bit. Okay, so we've identified that we're before the equivalence point, right? And so what we're going to do is we're going to subtract off of the equivalence point, aren't we? So we take 25 minus 24, and that means we have 1 milliliter until we hit the equivalence point, okay? And so this fraction remaining till the equivalence point is 1 of 25. The next thing we do is we put our original concentration in. That's this number right here. And then our dilution factor. Now we started off with 100 milliliters. We added 24 milliliters. So that means we're at 124, doesn't it? Okay. We go ahead and do the math now. That's going to give us 3.23 times 10 to the negative 4 molarity for our chloride concentration. Okay, the chloride that remains. Now, once we have that chloride that remains, well, we can then use the KSP formula to figure out silver. Okay? And so we take the silver's KSP, we divide it by that concentration of the chloride, and we get the concentration of the silver ion. We take the negative log of that value, and that will give us the PAG plus. Everybody get that okay? Okay. Anybody get confused, lost? Doesn't understand something? Okay, so the concentration of silver here is actually really negligible with the concentration of your unreacted chloride, even though we have a 96% complete concentration. And that's because that KSP is such a large one, such a 10 to the negative 10 number, right? We have such a very, very small KSP. We have such a large production of the solid. So what happens when we're at the equivalence point? Well, when we have exactly enough silver to react with our chloride, what's going to happen is we're going to be at that AgCl precipitation where we have that solubility equilibrium going on, aren't we? And so that's going to have the exact number of silver and chloride ions to give us the KSP, right? And so all we have to do is we just take this KSP. These numbers are equal, right? Because that's the equivalence point. They're stoichiometrically equivalent, okay? And so they're going to be the same number. We can put an x in there so that we can solve it easier, right? When we take those values, what we're going to do then is we're going to go x squared, right? We're then going to take the square root, and that's going to give us this number here, okay? That's just the square root of this. And all we have to do then is that is our concentration of our silver. That's also our concentration of our chloride. And so we are done. We just plug that into a negative log and we have our answer. Okay. And so plug it into negative log and we have 4.87. Note that this is going to be independent of your original concentrations and volumes. As long as you're at the equivalence point, they are equal. And so it actually doesn't matter what the original concentrations are at all. Okay? Because of the fact that they're equal, it automatically means that we have to be at equilibrium, right? So it's just going to be dependent on KSP. Okay? This is why, for example, this number here, remember how I was saying that this region shifts up and down, depending on this? This number here, this top line number, the highest possible state you can be in, that's dependent on your titrant. Because when we get over here, we basically have mostly pure titrant, right? We've added so much, we've overwhelmed everything else. Okay? This number here, your actual equivalence point, that's entirely dependent on your KSP or Ka, depending on what sort of system you're working at. Okay? And so what's actually happening here is this is shifting up, and it can bring this number with it. Okay? So this entire part of the curve here, except for the very front, shifts with it. Everybody kind of see that? Okay. Okay. So again, mathematically, the equivalence point is actually kind of the easiest. Conceptually, it's the one that tends to get people. Okay? Because remember, it's just dependent on your equilibrium, right? Okay, so after the equivalence point, what's happening after equivalence point? Well, they were equal to each other, right? Okay, after equivalence point, we add more and more of the titrant, right? And so what we're going to be doing is we're going to be incrementing towards a dilute titrant, aren't we? So we slowly increment towards having essentially a dilute titrant. Okay? And so all the solution contains all the silver added after the equivalence point. So we just have to figure out how much silver up to that, and then we just straight up add more silver. Okay? So let's suppose that we do the 27 addition. So we're 2 milliliters after equivalence point, right? And so we're going to take the moles of the excess. And so moles of excess is just the extra 2 milliliters times its concentration. And that gives us moles of excess silver. And that's all we need to do there. Okay? Now, the entire silver amount is going to be, well, that's going to be the largest amount of your excess silver, right? So that was 8 times 10 to the negative 5. Notice this number here was considerably smaller, wasn't it? Because of the KSP. Okay. So we take this excess silver, we divide it by the new volume because we've diluted it, haven't we? We added like 100 milliliters to that number, didn't we? And so we divide it by 127. That gives this new concentration of our excess. And notice that we have then our negative log right here. So notice that we can actually streamline this calculation now, can't we? Okay. We have the original concentration, and then we have the dilution factor. Right? And that's going to be our new concentrations for these excess silvers after our equivalence point. We've consumed everything up to the equivalence point. And so after equivalence point, it's just whatever we add is the amount that we have. Okay. Right here, this right here is before equivalence point. This is the equivalence point right here, right? And then this is the excess silver in this region right here, where we're adding more and more silver and we're getting further and further in excess. Okay. So whenever you look at these graphically, this is your nice little titration curve. You can actually figure out where we are very easily, can't you? See that? So before equivalence point right here, right? Equivalence point, always the sharpest region on our curve. And then after equivalence point goes back to being a gradual decline in steepness. You notice it's a very sigmoidal relationship. Your steepest slope is actually going to be the greatest value at this equivalence point. This will be the equivalence point itself is actually the inflection point here. If we were to take the second order derivative here, we'd get the 0 inflection point because we're inflecting around that point. And it's the maximum slope right here. Everybody go with that so far? Okay. What do you notice as you change concentrations, by the way? What happened to the broadness here? You get that same equivalence point, right? If you have low enough concentration, but your amount that you're going down here and then the amount you're coming up, those are much closer depending on that concentration of chloride, aren't they? See that? All right, so this is the auto titrator precision for this potentiometric titration of chloride. This would be your different concentrations, and this would be your relative standard deviations, your percent standard deviations. Notice as long as you have a reasonably high concentration, when you're doing a potentiometric titration, it's going to actually be pretty good. Those are actually pretty good relative standard deviations. Okay, basically as good as you would ever get from a BRAD. But what happens as your concentration dives off, goes down? Well, if your concentration decreases, then the potentiometric, i.e. electrical signal, is going to decrease, isn't it? Okay, it becomes harder to detect. Okay, and so your relative standard deviations are going to start going up pretty tremendously. Right? Okay, so let's look at how KSP affects this equivalence point right here. So again, our equivalence points here are actually going to be different because our KSP is different. So this is the iodine one right here. This is bromine. This is chloride. Right, see that okay? Yeah. So what we can see here is depending on that KSP, as we get these lower number KSPs, we're going to have these much larger, steeper drops-offs here. Okay, see that? Because again, we're shifting this entire portion down. Okay, this is dependent on the concentration of your titrant. This stuff here shifts down with your equivalence point. Okay, so let's go ahead and concentrate a concentration here. There's actually 3 ones I want you to try. I'll go ahead and leave this for next time. You start now. But you can do it over, you can leave now if you want and do it whenever you want. And then next time. That will be my next question to you all. Dun, dun, dun. Any